Welcome back to the part 2 of this video. In my previous video, I discussed summation by parts, and I uh, proved this theorem that if we have two sequences and the partial sum is given by this, then this estimate is true. I went quickly through the proof, and that was my first video. And also, I proved the Dirichlet test statement, which says if you have this condition met, then this series is convergent. And so that's not where I'm going today. I am going to be moving on to the next topic under this, which is going to be the absolute convergence. So I will start with the definition. A series given by this converges absolutely if the series given by this converges, which means if a series is given by an sequence an, I'm going to say that that series converges absolutely if by the time I put the absolute value on an, it converges. So let's see a theorem on this. What this theorem is saying that if this series sum of absolute value of an converges, then the series without the absolute value converges. Right? So which means, in other words, if the series converges absolutely, then the series converges. However, the converse is not necessarily true. I'm going to provide some examples to discuss why the converse is not true. But first, let's go through the proof. The proof is very short. All right, so the assumption given is that the series converges absolutely. So the sum of absolute value of an converges. By Cauchy criterion for series, what that means is that for every epsilon, there exists n such that this sum is less than epsilon for all mn greater or equal to n. Now, notice that I didn't put absolute value in outside the sum because what we are summing is already positive. For Cauchy criterion, you have this absolute value outside the sum. But in this case, each term of the sum is already positive. So when I add positive numbers together, I get positive number. So this is true from the assumption. However, we know that if we now have the absolute value of the entire of the series given by AK, right? This is now dealing with the series itself, not the absolute value. But triangle inequality helps us to be able to say it's less or equal to the absolute value of each term, addition of the absolute value of each term. And by the assumption, we know that that is less than or equal to epsilon. Therefore, the Cauchy criterion is also satisfied in this case, hence the sequence converges. So if I know that hence the series converges. If I know that a series converges absolutely, I am very guaranteed that the series itself converges. However, I will be giving an example where the series converges, but doesn't converge absolutely. And that will be coming in my subsequent videos. Thank you for this. This is where I'm going to call it up on this, and I'm going to be looking into the next topic under this, which is going to be rearrangement of terms in the series. Thank you.